What's up guys, how you all doing? Maybe on the internet you may have seen some things like this video. That thing is called a ZVS driver, and I was planning to do it for almost a year now. I've been planning to do this, so it's a long dream come true. And one subscriber asked me if I can do a ZVS circuit or a ZVS project, and well, his wishes came true. Now, but how does this ZVS driver work? Okay guys, this is the schematic of a ZVS driver. Now, you can see here, there are two MOSFETs, one here and two right here. The purpose of these two MOSFETs is switching. Well, as it is a transistor, then a transistor primary function is to switch. Now, anyway, these two switch each other, and these two diodes are for draining power through the gates and also to prevent any backward current flow, to prevent the MOSFETs from getting damaged. These two are the most important component in this circuit. A capacitor and an inductor connected in parallel creates a resonance circuit. I might have explained this phenomena in my previous video, but I'll make it clear. Here is a schematic for your ZVS circuit building. Okay, now this is the important thing in the ZVS circuit. This is a circuit consists of a inductor and a capacitor. Now two of them connected like this, and if we connect another battery source, which is momentarily, well, it will create a frequency just like this. Why? Now, this is called an LC circuit. An LC circuit consists of an inductor and a capacitor. Now, the two act as a two-way battery, if you know what I mean. Which I mean is, if we connect a battery source right here, which is very momentarily, if we connect it like this, both capacitor and the inductor become charged, both of them. An inductor will store charge in form of magnetic field, which will build up just like this. Well, this is a magnetic field, and the capacitor starts to store charge in electric field, which is this is plus and this is minus, both of them. This is plus, this is minus. But when we disconnect it momentarily, one voltage must flow to the other. Most of the time, the charge in inductor, which is just like this, most of the time. Now there is voltage L and VC, voltage in inductor and voltage in capacitor. Most of the time, voltage in inductor is much more than voltage in capacitor, usually. So the charge in inductor will pour to the, which means this will reverse, so the current will go through here. This will be current I. Now once it does that, all of this magnetic field will collapse, and eventually this will be no more. Wants to move the other way around to neutralize themselves. Apparently VL at this moment is 0, which all this that I showed represent this. I represented this part. Now current will start to flow. It will generate voltage, create a magnetic field, and repeating the cycle over and over and over again, which are represented right here. So this current will resonate and create an oscillation between this circuit, pouring one to the other. But while theoretically it will create a constant frequency, or a constant peak voltage, and with a given frequency. This, however, is not, because there is a factor which is called, well, resistance. Due to resistance, the voltage peaks of each time taken will slowly, well, damp, which we call a critical damping. So at this stage, in most of the time, this phenomena occurs in a very small second. probably in millisecond or even microsecond. So it will eventually oscillate and drop, and soon there will be no voltage. We can calculate this frequency using this formula. Resonant frequency is equal to 1 over 2 pi root LC. Well, L is inductance and C is capacitance. We're gonna need this to create our, well, ZVS circuit. Now let's get to the chase and solder our shit together.
A few moments later.
Okay guys, now I've made it. I've combined all the elements and components to make this. Yeah, these are two, if you can see it, two MOSFETs, well, two diodes, two resistors, two another inductors, three capacitors, and a coil which allows a huge amount of current to flow through it. This will be the place where I put an iron or a metal in and see if it can raise temperature. Oh, and also this is heatsink. Well, it helps for heat to dissipate evenly for MOSFETs because MOSFETs heats really quickly. Okay, now we've connected. I am now drawing about 10 volt and 3 amperes and 2 amps to the system, and we're gonna turn it on, and we're gonna use this metal to put it in and expect it to heat. Now let's turn it on.
A few moments later.
No, there's nothing. It's cold. There's no heat. Okay, what did I do wrong? It must produce heat, and it didn't. I don't know. Okay, let me adjust the things. Well, it turns out now I finally found the problem. The problem was in the, well, resonance frequency, because the capacitors that I used is about 0. Or in other terms, about 4.3 microfarad, which is not sufficient. What do you know? Well, I calculated the resonance frequency. Well, the frequency, well, about 20,000. It must be 20,000 for the ZVS circuit to work efficiently. But apparently mine is much greater than that. Well, the optimum frequency that I told you was, again, 20,000. More than that or less than that would not, well, work effectively. Maybe that's why. Well, that did not turn out well. What can I do other than melting a metal? Well, we could mount the external, we can mount this coil onto a flyback transformer's coil and expect a huge amount of voltage. That's what I want to do. So let's do it. All right, let's do this. Whoa. Damn. Wow. Damn. Wow. Let me bring it closer so you can see it. Wow. I'm pretty sure that's cool. Maybe that kind of voltage, maybe around, wait, let me see it. Okay, that's really big. Maybe it's around 60,000 volts, maybe. Let's say this is around 2 centimeters. There's already an arc. Yep, that is definitely 60,000 volts. Wow. Okay. You can see the arcs, you can see the coronas. And when I make it closer with the transformer, I think the transformer has its own capacitor or some kind. Wow. That is great. Well guys, thanks for watching. And don't forget to share, subscribe, and comment anything you like below. And see you in a bit.